Hey, hi everyone. So welcome to Fundamentals of Wireless Communication tutorial. So I'm your TA Rubina Afrin, Prime Minister Research Fellow from IIT Hyderabad. So today's topic are basically information theory. We will be discussing some topics of information theory, and then we will move on to some questions, and later then we will see how to derive the capacity of MIMO channel from the information theory perspective. So that's all we're going to cover in this class. Let's start. So the first topic that we will be discussing is entropy. So entropy is like determining how much random any source is. So like suppose you have a text file. Huh? So if you look at any text file, all the characters will be uh, random. So there will be a probability of occurrence associated with each alphabet. But if you see any text file, the occurrence of the letters is not deterministic, right? So it's totally random. So for these type of scenario, we will be using entropy. So entropy of any source will give its inherent randomness. Like we are discussing about the text file, if there are random letters on the text file, then we know that how much probability every letter is having, and from there we will be knowing how much are the minimum number of bits required so that we can encode the text. Like every thing in compression is any compression sequence is determined by like number of bits required to encode the source. So we will see more about it. Let's consider that we have some alphabets that is a finite size, like suppose x1, x2 up till xn. So in mathematical terms, entropy is defined as h of x equal to summation I equal to 1 to n probability of xi log to the base to 1 upon pxi. So entropy, since entropy is the order of randomness, we can determine maximum amount of compression that can be done on a source from entropy. So now we will see some more concepts. See, uh, for any source, entropy is given by summation x. Let's x belongs to some big set of alphabets. That is this x. This is px into log to the base 2 of px. This we saw right now. This unit is in bits. But if it is given as px ln px, then the unit will be nats. So we will be using both of these interchangeably as per our convenience. Okay, so now from here we can see that probability, this px will always be in between 0 to 1, right? So it is positive. And then we have, since px is in between 0 to 1, what will be the range of log of px? Log of px will be certainly less than equal to 0, right? So minus log of px will be greater than 0. So that means that both the product will be greater than 0. So we always have entropy greater than equal to 0. Okay. Then we have joint entropy. So suppose if x and y are a pair of random variables, then the joint entropy is given by h of x y equal to minus x belongs to big X, that is the set of alphabets, and then y belongs to big Y, pxy log to the base 2 of pxy. So we are discussing all these concepts because we will be needing them for the capacity determination. So I will not be going into very deep concepts here. You can maybe refer to the information theory classes or can refer to some book, but we will be covering whatever is required here. So the formula for joint entropy is this. Then we will move on to conditional entropy. So h of y given x is given by summation x belongs to alphabet x and summation y belongs to big Y. P of x into p of y given x log to the base 2 of p of y given x, which if you calculate this minus sign will be there. So probability x belongs to x, y belongs to y, and then this is the formula for the joint probability distribution, right? So this is pxy log to the base 2 of py by x. So this summation pxy log to the base 2 of py by x, this can be written as minus of expectation over pxy of log to the base 2 of y by x. Okay. Next we will talk about the chain rule. So chain rule states that the joint entropy hxy, this is given by entropy of x is conditional entropy of y over x. Okay, so we will see how it is done. So we have the LHS as h of xy. Now we have seen that the joint entropy is given by this formula. So maybe I'll just copy it once. Okay. So we have this. Now we will write it as summation x belongs to x, y belongs to big Y. This we can write, we can use the formula for the joint probability distribution. So we can write it down as, or maybe we can break this one. So that will give us the standard result. So that we can write it as joint distribution is given by probability of x into probability of y by x. So we can break this into two summations pxy into log to the base 2 of px minus summation over pxy log to the base 2 of py by x. Okay, so this will be given as hx plus this is hy conditional on x. So like this. And if you write it as p of y into p of x by y, then it will come as h of y plus h of x by y. The next thing is relative entropy. So relative entropy gives the distance between two distributions. Like two probability distributions are there. Relative entropy is like we are getting the distance between the two distribution. It is also known as Kullback-Leibler distance. We'll write it down. Kullback-Leibler distance. So relative entropy is measure of distance between two distribution. Kullback-Leibler distance is also denoted by D. So if we have two distributions px and qx, so we can write it as dpx qx, or also it is written as dpq. So this is given by summation x belongs to big X px log of px by qx. Okay, so now this is summation and then px into fx. So this can be replaced. This is expectation. So this is expectation over px of log of px by qx, right? So d distance between p and q is not equal to distance between q and p. So these and all are important for your assignment questions or maybe in exams also. So then one important concept is of mutual information. So mutual information is the relative entropy. Okay. Between what? Between joint distribution and product distribution. Okay. So it is the relative entropy. Relative entropy means Kullback-Leibler distance between joint distribution and product distribution, right? So if we have two random variables, suppose two random variable x and y, they have the pdf. This is the joint distribution pdf. Okay, and then probability distribution functions given by p of x and p of y. Okay, this is the joint one and these are the marginal one. So according to the definition, what is ixy? See, what is d between p and q is px log of px by qx. So here we have to find the distance between pxy and product of px and py, right? So like previously we have written like that only, p of xy into log to the base 2 pxy by px into py. Okay, here x belongs to big X and y belongs to p5. So there is the distance between joint distribution and product distribution. Okay, now we can modify it. This is summation over pxy log to the base 2 of. Now we can break this joint distribution in terms of uh, relative distribution, right? So we can write it as p of x into p of y by x divided by p of x into p of y. Okay, so if we do more calculations, we will reach to pxy. This is cancelled. Log to the base 2 of py by x minus log to the base 2 of py. So this minus log to the base py into pxy will be h of y, and the other term is with plus sign, right? So for the entropy, this will go in minus. So this will be h of y minus h of y by x. Right. Now here we have broken the joint distribution as px into p of y by x. We can do it as py into p of x by y, right? So when you do like that, then the information you can write as h of x minus h of x by y. Okay. Now just now we have studied chain rule, that h of x y is h of y plus h of x by y. So from here we can write, suppose h of y by x we will take as h of xy minus h of x, right? So if we put that, then h of xy will be in minus sign and the other hx will be in plus sign. So overall it will be h of x plus h of y minus h of xy. So these three are the important formulas for mutual information. Okay, I hope that will be clear. And then one important trick to remember this formula is, you can remember it with Venn diagrams. This is for hx, this is for hy, and this is information between x and y. Okay, so this whole is hy, then this part is hy given x, and this part is hx given y. Now you see ixy is first thing hx plus hy minus hxy is clear. I hope that is clear. And then h, this hy minus hy by x. Right. So this is hy minus hy by x, and similarly hx minus hx by y will leave this one, right? So this is hx minus hx by y. So I really hope we can take some questions around, and then we will move on to discuss Jensen's inequality. So this is the first question. Here the joint distribution is given, right? Pxy is given, and then we have to find hx and hy. So first I'll write the formula to know what we need. So hx is px log to the 2 of px. right? So from here we have to find px. So this is probability x equal to 0 log to the base 2, there is a minus sign here, probability that x equal to 0, then minus probability x equal to 1 log to the base 2 probability that x equal to 1. This will be hx, right? So probability that x equal to 0 is 1 by 3 plus 0, right? That means x equal to 0 when y equal to 0 plus x equal to 0 when y equal to 1, both cases. So this is given by the sum of this row. So we have, I'll write it down here, probability that x equal to 0 is 1 by 3, right? Probability that x equal to 1 is 2 by 3, the sum of this and this. Okay, then we have probability that y equal to 0 is, so y equal to 0 is this column, right? So that will be summed, and then probability that y equal to 1 is the sum of this column. So that is 1 by 3. So now we will put it in the formula for hx. So that is minus 1 by 3 log to the base 2 of 1 by 3 minus 2 by 3 log to the base 2 of 2 by 3. So that when calculated will give us 0.918. Then again for h of y, same formula will be there, minus probability y equal to 0 log to the base 2 probability y equal to 0, and then minus probability that y equal to 1 log to the base 2 probability y equal to 1. So since this is very interchangeable, right? Like probability y equal to 0 is 2 by 3 and then it is 1 by 3. So the data will be the same. So here also it will be 0.918. Okay. So the value of hx and hy are equal, and that is equal to 0.918. Okay, so we will move on to the next question. Here we have to find information of x and y. So we will take the formula hx minus h of x given y. You can use hy minus h of y given x, or maybe you can use hx plus hy minus h of xy, right? So we will be using this one, we will be proceeding with this one. Hx we know already, right? Now we have to calculate hx by y. So hx given y will be given as probability that y equal to 0 h of x by y equal to 0 plus probability that y equal to 1 into h of x by y equal to 1. Okay, so probability that y equal to 0 is 1 by 3, and probability that y equal to 1 is, this is y, so y equal to 0 is 2 by 3 we have calculated here, right? Okay, plus 1 by 3 h of x when y equal to 1. Okay, now we know the conditional distribution. So hx when y equal to 0 is given as minus probability that x equal to 0 when y equal to 0 into the base 2 p x0 by y0 minus probability x1 when y0 into log to the base 2 probability of x1 y0. Okay, Now see probability that x equal to 0 given y equal to 0. This is equal to, no, we have not been given this one. We have been given probability that x equal to 0, y equal to 0, right? We have been given the joint distribution. So we will use our formula. So from the figure, we can see probability that x equal to 0 and y equal to 0 is 1 by 3, right? So we have 1 by 3 and probability that y equal to 0 is 2 by 3. So that gives us 1 by 2. Okay. Then probability that x equal to 1, y equal to 0. This will be given by probability that x equal to 1, y equal to 0 divided by probability of y equal to 0. So when y equal to 0 and x equal to 1, we have to find it from the table. Y equal to 0, x equal to 1 is again 1 by 3. So it is 1 by 3 by 2 by 3. That is again 1 by 2. So we computed these two. Now we have to put in this one, right? So h of x given y equal to 0. This will be given by minus half log to the base 2 of half minus half log to the base 2 of half. So this is 1. Okay, now we found out this one. Right? Now this term we found out already. This term we have to find. We will use the same procedure like the previous. So h of x when y equal to 1, when you do the calculations, then you will find out that it is equal to 0. Okay, so now you have to do this. You have to do the calculations in similar manner, right? Here you have to take x equal to 0 when y equal to 1, and then x equal to 1 when y equal to 1. So entropy of x given y is 2 by 3 h of x by y equal to 0 plus 1 by 3 of x h of x by y equal to 1. So this one is 0. So this is 2 by 3 into this one is 1. So this is 2 by 3. This is 0 0.667. Okay. Now we have to find the information, right? This one we have, and now this one we calculated. So we will very quickly find ixy. This is given by h of x is 0.918, right? H of x minus h of x by y. So this is 0.918 and this is 0.667. So this will give us 0.251 bits. Okay. So the answer is C. Now this one also we can handle right now. So this is based on simple formulas only that we have discussed right now. So which one of these will be correct? H of xy equal to h of x plus h of y by x, right? And then this is the chain rule, right? We have discussed this. And then now these two things you see, point number 2 and point number 4. So point number 2 says relative entropy measures the distance between two distributions. And the point number 4 says Kullback-Leibler distance measures the distance between 2 points. Now we know relative entropy and Kullback-Leibler distance are the same, and it measures the distance between two distributions, not 2 points. Always two distributions. So here 1 and 2 are correct, right? So that is why the answer should be A. Okay, then this one also we can do. We have been given a discrete random variable x and the PDFs are given. Now we have to find the entropy of this variable. So this is very straightforward, right? Okay, then minus probability x equal to 2 log to the base 2 px equal to 2. Then the next one is x equal to 4 log to the base 2 probability of x equal to 4. Then the next one is okay. So this is minus 1 by 2 log of 1 by 2 minus 1 by 4 log to the base 2 of 1 by 4. This is very famous problem of compression in information theory. So this will give the entropy as 1.75 bits. Okay. Okay, then this question we will discuss when we discuss the continuous random variables. Okay, I think now we are ready to move on. So we have discussed till mutual information, right? Now I would like to discuss Jensen's inequality. Jensen's inequality is also used in the capacity derivation in digital communications. Here also I think we will see the Jensen's inequality. So better we discuss it right now. So first of all, we know convex functions, right? So if a function fx so we have a function fx is convex over any interval ab, if for each x1 x2 that belongs to ab, f of lambda x1 plus 1 minus lambda x2 is less than equal to lambda times of f of x1 plus 1 minus lambda times of f of x2. Here lambda is lying between 0 to 1. Okay. So I'll just describe what is meant by this. So suppose two intervals are there, a and b, and we have 2 points x1 and x2 that are lying in this interval. Suppose this is the plot of fx, right? So this one is f of x1, right? And this one is f of x2. Okay, so the value of this function will always lie between the chord joining f of x1 and f of x2. Okay, the value of this will always lie below the chord joining the f of x1 and f of x2. Okay, so this is the definition for convex function, and if any function is strictly convex, that means that uh, the equality holds. So for equality to hold, lambda would be either 0 or 1, that is like the two edge points. If lambda is 0, then this is the value for this term, right? And if lambda is 1, then the value for this is f of x1. Okay. Now we define Jensen's inequality for any convex function, right? So if f is convex, and x is a random variable, then expectation of fx is always greater than equal to f of expectation of x. Okay, this is known as Jensen's inequality. And if the function is strictly convex, then equality will hold. That is x equal to ex, x equal to expectation of x. What does that mean? That means that x is constant, right? Okay. Then one more concept is so if we have two probability distribution functions, px and qx. Okay. For x belongs to some big alphabet x, then we know this, right? That distance of two distance between two probability distribution functions is always greater than equal to 0. But uh, the equality will be if px equal to qx. Okay. So equality will hold if and only if, that is I if f, px is equal to qx for all x. Okay, so if we need to prove it, I think we can prove it, but maybe we will see some questions before that. Okay, this question we can see. We have a discrete random variable x. The entropy of x will be maximized if x follows. So if we have a discrete random variable x, the entropy of x would be right. So entropy is randomness. Okay, so randomness will be maximized if what? If uh, all the px is uniform, like all the probability, all the symbols are occurring with uniform probability, right? So for any discrete random variable, the entropy will be maximized if x follows the uniform distribution. Okay, this is not the case for continuous random variable. That is when the uh, that is when the x follows Gaussian distribution, but that is another case. We will discuss it. So uh, here the entropy will be maximized if x is uniform distribution. You can take two variables or three variables, and then you can differentiate x. You can differentiate the entropy with respect to px, right? And then you can see that the entropy will be maximized only when the probabilities are equal. Okay, so we will move on. I think this question we can address. So Hx is always greater than equal to 0, that we know entropy is never not, entropy is never negative, right? So this one is true. Okay, then another thing is I of xy information, that is equal to h of x minus h of x by y, right? And information, mutual information is the relative distance, relative entropy between joint distribution and product distribution, right? So the relative entropy is always positive, correct? So in information is also positive, mutual information is always positive. So ixy is always greater than equal to 0. So we can write hx minus hx by y is greater than equal to 0. That means hx is greater than equal to hx given by. Okay, so now we know that the second statement is incorrect, first statement is correct. Then information ixy greater than equal to 0 with equality if and only if this. No, information is always greater than 0. Information is always greater than equal to 0. It is always positive. So this is not correct. And then we just have seen that dp and q, Kullback Leveler distance between px and qx, is always greater than equal to 0 with equality if px equal to qx. Maybe we can do the derivation, but then that is part of information theory, so you can maybe look up to it. So I'll just mention the statements. So from here, first and fourth are correct, right? So the answer would be C. Okay, and this question also we can address. So this is very straightforward question. Any function fx is said to be convex over an interval AB if for every x1 x2 belongs to a comma b, like x1 and x2 lies in the interval a and b, and lambda is 0 and lambda is in between 0 to 1. So this is the definition for convex function that we have discussed uh, just now. So that is f of lambda x1 plus 1 minus lambda x2 is always less than equal to lambda times of fx1 plus 1 minus lambda times of fx2. So this is the answer. Now you see this question. Suppose we have x and y as random variables. Ixy denotes the mutual information. Then which of the following statements are true? Now again you see, take the Venn diagram. This is hx, this is hy, this is hy given x, this is hx given y, this is ixy, right? So you know hx plus hy minus hxy by hxy. Then it is hx minus hx by y, right? And then hy minus hy by x. So 1, 3 and 4 are correct. Okay. Okay, so we will move on to the discussion of other concepts. Okay, so till now we have discussed for discrete random variable, right? So now we have for continuous random variable. Hi, so sorry for the interruption. So now we will move on to the continuous random variable case. Okay, so everything is similar. So where we have computed entropy, now we will do differential entropy. Okay. So before discussing differential entropy, we'll just discuss some concepts related to continuous random variable, and then we will move forward. So if x is a random variable, then the CDF will be probability that x is less than equal to x, right? From here we find the PDF is this. Okay. And if integration minus infinity to infinity fx equal to 1, then fx is PDF of x, right? Okay. Then we have support set. Support set is for different continuous random variables as well as discrete random variables. Okay. So support set is set of values where fx is greater than 0. Okay. So this I mentioned for continuous case, but if discrete case is also there, then we have the countable set, right? Currently we have uncountable because we have the continuous set, but if discrete is there, then we will have the continuous set, discrete set, like countable number of sets. So this is the support set. Then we will move on to differential entropy now. This and all I discussed because we will be using it in the further. So we have differential entropy. So differential entropies are denoted by small h. So this is given as integration over support set because we are taking support set here, like the set where the fx is greater than 0. Okay. So fx log of fx. Why we are taking the support set? Because this term inside the logarithm we need it to be positive, right? In the discrete case also, we were taking probability distribution function that is positive. So that is why we will be integrating it over a support set always. We won't be integrating it over the entire range. Okay. So this is the formula for differential entropy. This h is a function of fx, right? So sometimes we will be denoting it as hf. Okay. Now suppose we have a uniform distribution. So for uniform distribution, suppose this is from 0 to a. This is 1 by a. What will be the entropy in this case? Integration 0 to a 1 upon a log 1 upon a dx, right? So this is equal to, this will be integrated to a. So this is log of a, right? Now suppose if a is less than 1, then entropy is less than 0, right? So contrary to entropy, differential entropy can be negative. Okay. Then one more important concept is for entropy of normal distribution. So slowly we are moving towards the capacity part, right? Now we are moving to the entropy of normal distribution. By the time we will be discussing capacity, we will know that the whole flow is for the capacity of MIMO channels. Okay, so now we are discussing normal distribution. Suppose X have a PDF of 5x that is given by 1 upon square root of 2 pi sigma square e to the power of minus x square by 2 sigma square. So the entropy for phi would be minus of phi ln phi. This will be equal to integration of, now ln phi would be log of this plus this, right? So this will be equal to phi x into minus x square by 2 sigma square minus half ln of 2 pi sigma square. Okay, so this square root of 1 by 2 is coming outside as minus half. Then dx. So this minus and minus will go as plus x square by x dx by 2 sigma square plus half ln 2 pi sigma square dx. So this is h of phi. Okay, here you see this term is constant, right? So this is half times of integration of phi x dx. Now phi x is PDF. So integration of PDF is 1 always. Okay, and then this term you see. So this is 1 upon 2 sigma square. And then can we write it as expectation of x square, right? Plus 1 by 2 times of ln 2 pi sigma square. And then normal distribution, right? So it is 0 mean and the variance is 1. So what is the value of ex square? This is 1. Okay, so we can write it as 1 by 2 sigma square is ln e. Oh, no, sorry. The variance is sigma square. I did not see that. So this variance is sigma square. This sigma square and sigma square will cancel. So now we have half of, we can write as ln e plus half ln 2 pi sigma square. Okay, this we can write as half of ln 2 pi e sigma square. So since we are using ln here, so the unit is nats, right? So here we are using ln for the convenience because that is e to the power, right? Now we can easily replace it with log to the base 2 pi e sigma square, and we will get the unit as bits. Okay, so this is the entropy of normal distribution. Okay, now again I will be writing down some formulas for joint differential entropy. These results are very same as the discrete case, so there is nothing much to discuss here. So for joint differential entropy, we have suppose a set sequence of x1, x2 up till xn with PDF as of x1, x2 up till xn. Then the joint differential entropy, this will be given as integration joint PDF into log to the base 2 of f x1, x2 up till xn dx1 up to dxn. Okay, So this is the joint differential entropy. Then we have the just like conditional entropy was there. Here we have joint conditional differential entropy. Right. So here again, I'll just write the formulas very quickly. So hx given y is given as fxy times of log f x given by dx dy. Then again we can write like we have done in the probability. Okay. So when we substitute it here, then we can see that this will be the sum of fxy into log of fxy minus fxy into log of fy, and then we will take the minus sign inside. So again it will come as h of xy minus h of y, and this is since joint distribution we will always write it with the small letters. So this is h of xy minus h of y. This is for joint conditional distribution. Okay. So now we have discussed the entropy for normal distribution, right? Now we want to discuss the entropy for multivariate normal distribution. Okay. So suppose we have a multivariate normal distribution where the variables are x1, x2 up till xn. Okay. We have a mean of mu and covariance matrix k. Okay. So since there are n symbols, so mean is a vector and covariance matrix is like matrix only. Okay, so this multivariate normal distribution is denoted as n with mu mean and k variance. This joint distribution has probability distribution function is f of x equal to 1 upon square root of 2 pi to the power of n modulus of k to the power of 1 by 2. And the determinant of k to the power of 1 by 2. So k is a matrix here. Then e to the power minus half. For the single variate we are taking x square, right? Here we have the x minus mu transpose k inverse and then x minus mu. Okay. Now we are aiming to find the entropy of this. So write down the formula as usual. That is fx into log to the base 2 of fx integral with the minus sign. Now log to the base 2 fx you see. So we will take ln here, okay, and the unit we will take in nats, and then later we can change it into bits. So ln fx we will take, right? So here we will be having fx into ln of fx will be two terms, ln of this and then this term. So I'll write this one down, minus ln 2 pi to the power of n determinant of k to the power of 1 by 2, and then this term will be 1 by 2 and x minus mu transpose k inverse x minus mu. See, n variables are there, na? So this x will be n cross 1, right? So x minus mu transpose will be 1 by n. This is n by n and this is n by 1. So the result is this is n by 1 and then this one is like one single term 1 by 1, right? And then dx. Now you see this one is constant, right? And apart from this we have integration of fx dx. So that is equal to 1 because integration of pdf is 1. Okay, so the first term we can separate. This first term we will be having is half ln 2 pi to the power of n determinant of k plus. Now we see the second term. We have fx x minus mu transpose k inverse x minus mu dx, right? So this is like integration of fx into this dx. So we can write it in the terms of expectation, right? So we take each of the term. So this is the same and then this will be expectation of ij, then xi minus mu I into kij inverse into xj minus mu j, right? So since expectation is linear operator, this can go inside. So this is half summation ij and this is also like single term, right? So we can write it as xi minus mu I into xj minus mu j into kij inverse. Okay, so now you see this term and this term expectation I forgot. So these two are the random variables, right? Kij is the constant, so we are putting expectation on the random variables. So this is again coming as kij, right? This is the covariance. So now we can write it as this is the same term repeated, half ln 2 pi to the power of n determinant of k plus half then expectation of kij inverse. This is summation over ij. Okay, so now these will go to n terms, right? So this is half times of n because this is 1 and this is half ln 2 pi to the power of n determinant of k. So this half n we can write as half times of ln e to the power n, right? So we combine both of these and then we will have entropy of multivariate normal distribution. This as half of ln 2 pi e to the power of n determinant of k. This is in nats, so obviously we will do half log to the base 2 2 pi e to the power of n determinant of k. This we will get in bits. Okay, so this is also one important thing. So we are going after Gaussian distribution because we will be having Gaussian channels, right? Gaussian noise we will be having, then complex Gaussian channels or Gaussian channels, AWGN channels. So that is why we are doing all this. Okay, so this is HX. So here you see, if we have a multivariate Gaussian distribution, then this is the case. But if we have a multivariate complex Gaussian distribution, then I'll skip the calculations, but in the PDF for multivariate complex Gaussian distribution, then we don't have the two factor here, right? This one is not there and this one is not there. So in the final answer also the two factor is not there. So we have for multivariate complex Gaussian, we have hx is half, no sorry, not half. This is log to the base 2 pi e to the power n determinant of k in bits. Okay. So this is for multivariate Gaussian distribution. Right. Then we have the relative entropy and mutual information. So relative entropy, this is given by this is very self-explanatory, right? We just use the integration because this is for continuous random variable. Then we have mutual information. What is mutual information? It is the distance between joint distribution and the product distribution, right? So again we will have Ixy is integral of fxy log to the base 2 of fxy by fxfy. Okay, this is dx dy. Here also Ixy is hx minus hx by y or hy minus hy by x. Okay. And then this we have already discussed that this distance is always greater than equal to 0. So information is always greater than equal to 0. Now suppose we have a random vector x. This x belongs to Rn. That means it is n cross 1 vector. Okay, this has 0 mean and covariance of k. K that is equal to expectation of x transpose. So this is covariance matrix. Then we say that entropy is bounded by half log to the base 2 of 2 pi e to the power n determinant of k. Okay. So this we know that this is the entropy of normal distribution, right? Multivariate normal distribution. Here x is any other distribution. Okay. So for any other distribution, the entropy is always upper bound by half log to the base 2 of 2 pi e to the power n determinant of k. Okay. So what do I mean to say? This determinant of k is on the inside. So what do I mean to say is that entropy is maximum when x is 0 mean like normal distribution, right? So I'll write it down just that entropy is maximum if and only if it belongs to normal distribution, right? So multivariate Gaussian distribution is giving the maximum entropy than any other distribution with the same covariance. Okay. Similarly for complex Gaussian, okay. So for complex Gaussian, we know that for complex distribution, the entropy is upper bound by this half is not there, right? Log to the base 2 of pi to the power n determinant of k. Okay. And the upper bound reaches when the distribution is 0 mean complex Gaussian, circularly symmetric complex Gaussian. So the multivariate normal distribution is having the maximum entropy. Okay. And for complex distribution also, the multivariate complex normal distribution has the maximum entropy. Okay. So this is one important point that you have to remember. Now slowly we are transitioning into the communication system for information. We are going now. So we have this topic is asymptotic equipartition property. So you see, we have IID random variables. Okay, x1, x2, and so on. These are the IID random variables. So PDF is px. Okay, then this asymptotic equipartition property, this states that minus 1 upon n log of p x1 x2 up till xn. This tends to hx if n is large. Okay, this comes from the law of large numbers. I'll discuss how. So since we have the IID random variables, right? So the joint distribution is the product of distributions. Okay. So this product distributions, when log is taken, then it will go to sum, right? So we can write it as sum 1 upon n summation I equal to 1 to n up to the base 2 pxi. Okay. Now you see, this term we can write as expectation, right? Minus of expectation. How this goes from law of large numbers, big law of large numbers, because if there are lots of this n is very large, then the summation divided by n tends to expectation. Okay, so now this we know minus expectation of log px. This is given by summation I equal to 1 to n px log px, and this is equal to hx, right? So that is how this term is tending to hx if n is very large. Okay. Now, if n is very large, then we have this statement, right? Okay. From here, we can say log of p x1 x2 up to xn is equal to minus n hx, right? So from here we can say that the joint distribution px1 x2 up till xn, this is 2 to the power of minus n hx. Okay. So what is the significance of this thing that we are discussing? This x1 x2 up till xn is some sequence, right? And this p x1 x2 up till xn is the probability that this sequence is occurring. Okay, so for any long sequence, the probability that that sequence is occurring is given by 2 to the power of minus n hx. Okay, so for any arbitrary sequence of length n, the probability of that sequence to occur is 2 to the power of minus n hx. Okay, like suppose so I hope this much is clear. Like any arbitrary long sequence is there, like 0 1 0 0 1 0 1 0, like that. So there will be some occurrence of um, probability of occurrence of 1 is suppose p1, probability of occurrence of 0 is suppose p0. Then number of ones would be in p1 if n is very large. Similarly, number of zeros would be in p0, right? So in this case, entropy would be equal to so nx would be equal to um, log of p1 to the base of p1 to the power of np1 plus log of p0 to the base to the power of np0. So we can combine it as right. So this p1 to the power of np1 into p0 to the power of np0. This is what? This is the probability of occurrence of the sequence, right? So p1 to the power of np1 into p0 to the power of np0. This is given by again 2 to the power of minus nhx. Okay. So these sequences, we can group these sequences as typical sequences. Typical sequence denoted by ATN. This is like this contains the sequences that have very high probability, that is 2 to the power of minus nhx. So we have suppose a big set. This is x, and then we have inside it one smaller. This is a typical set. Okay, so typical set is a set of sequences, these long sequences. So all sequences in typical set are equiprobable with probability how much? 2 to the power of minus nhx. Okay, so can we tell how many sequences are there in this typical set? So number of sequences will be, since they are equiprobable and the probability is 2 to the power of minus nhx. So number of sequences would be 2 to the power of nhx. Okay. So typically the number of sequences is bound by one upper bound and lower bound. So I'll just mention it here. So the upper bound is 2 to the power of nhx plus epsilon, and the lower bound is 1 minus epsilon e to the power of nhx minus epsilon. Okay, we won't be getting into detail of this one. So all the background that we had to establish for communication scenario is done now. So now suppose we have a transmitter and we have a receiver and we have a channel in between, right? So the transmitter is transmitting long sequences. Okay, that is why we were discussing sequences till now. The receiver is receiving the sequences. Okay, now for every sequence, this can go into errors, right? So every sequence can generate a set of output sequence because there will be noise added. So some bits can be flipped, right? Like suppose we are sending 001, it can be received as 0010100111011 anything. So this will generate a set of outputs, right? Now what we want in a communication system is that whatever is sent can be decoded perfectly, right? So suppose we have a sequence. So this is the first input sequence x1 in this x1 of length n. Likewise, this is the second, third, like that. So each sequence will be generating a set of output, right? So this sequence will have some elements in output sequence. Again, this sequence have some elements in the output sequence. Right. So suppose if any sequence is there, so for each sequence, number of sequences in y, like each sequence will generate 2 to the power of minus nhx, right? So for each sequence, number of sequence generated in y would be equal to 2 to the power of nh. This time it would be y given x because x we already know, right? And total number, this is the number of sequence generated for each x, like these ones. Okay, and total number of such sequences in y would be there, right? So total number of such sequences is 2 to the power n hy, right? So for better performance, what we want is that separated sets should be there and we should have maximum number of distinct sequence, right? So this is sequence generated for each sequence in x, and this is the total number of sequences. So how many number of different sequences would be there? This would be equal to 2 to the power n hy by 2 to the power n hy by x. So this can be written as 2 to the power n hy minus hy given x. Right. So for maximizing the number of different sequences, because we want better performance, so we have to maximize the number of different sequences. So this term should be maximized, right? So what we have to find the maximum of hy minus hy by x. What is this? This is information. Maximum of ixy. Right? This is the mutual information between x and y. Right. So we want to get as many sequences in y, right? So for that we have to maximize the mutual information between x and y. This is how we define the channel capacity. Okay. So channel capacity is, and that is why we are discussing the information theoretic concepts, because at the end the channel capacity is maximum of ixy. Okay, so capacity is given by maximum of information over all the distribution of source. Right. So this is the capacity. And now from the previous discussion, we know that the mutual information is maximized when uh, when uh, the distribution, the effects, the distribution is zero mean complex Gaussian, right? Okay, so now we can handle this question now. So we have the transmitter that generates a sequence of n number of symbols. Okay, so this statement uses typical sequence can be formed if the symbols are equiprobable. That is correct, because we have just discussed now, right? Okay, if the symbols are equiprobable, then long symbols are equiprobable, and then only typical sequence can be constructed. And each of the symbols will occur with the probability of 2 to the power minus nhx. That is also correct. And then each of the symbols will no, this is not correct, and this is also not correct. So 1 and 2 are correct. Okay. So now we can see this question as well. So here we have x as 0 and 1, and the value of dpq and dqp we have to calculate. So this would be equal to, okay, so this distance between two distributions only, right? So p of x equal to 1 log to the base 2 x equal to 1 by q x equal to 1. So now you see probability that x equal to 0 is 1 by 4, right? Then log to the base 2 probability of x to the probability that x equal to 0 upon q when x equal to 0. So here we will have 1 by 4 upon qx is 0 when probability that qx is 0 is 2 by 3, right? Then here we have 1 by 4 log to the base 2. Now probability x equal to 1 is 3 by 4, and then log to the base 2. Then px equal to 1 is 3 by 4, and then qx equal to 1 is 1 by 3, right? So this when you will calculate, it would come as 0.5237 bits. Okay. Similarly, for calculation of dqp, this would be q0 log to the base 2 q0 by p0 plus q1 log to the base 2 q1 by p1, right? So then this would be 2 by 3 log to the base 2 then 2 by 3 upon 1 by 4, right? Plus then this would be 1 by 3 log to the base 2 1 by 3 upon 3 by 4. So when you calculate it, it will come as 0.5534. Okay, so these and all are done. Now evaluate differential entropy. This is now easy. So this, just put it in the formula, 0 to infinity fx log to the base 2 fx dx, right? So this is minus 0 to infinity lambda e to the power minus lambda x into log to the base 2. Now since there is e to the power, so you can use ln and then get the result in that. So maybe we should write it like this, ln lambda e to the power minus lambda x dx. This is in nats. Okay, so this would go as 0 to infinity lambda e to the power minus lambda x, and then this ln lambda minus lambda x, and then dx. So this would be constant, and then one is this integration, one is integration of x e to the power minus lambda x. So first integration is easy, second integration you have to do by parts. So the answer would be 1 minus ln lambda max. Okay, so we can write it as ln e by lambda nats, right? So if you write log to the base 2, then it is in bits. So this is log to the base 2 e by lambda bits. Okay. This we will be discussing after discussion of the concepts. Now in this question, you see, we have the covariance matrix given and the mean is given. We need to find the differential entropy of fx, right? So we have it is a bivariate normal distribution, right? So for normal distribution, we know that the entropy is given by, and this is bivariate normal distribution, not complex normal, complex Gaussian, it is Gaussian. So this will be given by half log to the base 2 2 pi e to the power of n. N we have as 2, and then determinant of k, right? Now calculate determinant of k. That would be 5 minus 0.08, that is 4.92, right? Now put it in the formula. So when you put it, this will be half log to the base 2 pi e square into 4.92. So this will come as half into 10.487, that is 5.243 bits. Okay, so the answer is A. Correct. Now MIMO channel we will discuss, and then two questions are there. So we will see. So now we have seen that the capacity is maximum of the mutual information, right? Now if we consider a Gaussian channel, so if we consider a Gaussian channel, we have a input xi that goes to the channel, and noise 0 mean ni variance complex Gaussian noise is added, and the output we are getting is yi. So at the transmitter, we have already discussed previously also that we have the power constraint, right? So suppose xi is the sequence x0 x1 up to xn. in what way the power constraint is? Okay, so power is limited. So the capacity is given as maximum of mutual information, right? And we have the constraint now such that expectation of x square is less than equal to p. Okay, so the information we have is h of y minus h of y by x. Now we know y is x plus z, right? So when we write this as x plus z, it will come as h of x by x plus h of z by x. H of x by x is 0 and h of z is independent of x, so that is h of z only, correct? So this will be coming as h of y minus h of z. So this z is noise, right? This z is complex. This z is Gaussian noise. So we know the entropy of this, right? So these and all are again continuous. So we have to write it in small caps. So this is h of y by x. Like that we know h of z. This is half log to the base 2 pi e and then m. So now expectation of y square is expectation of x plus z square, right? This can be written as expectation of x square plus expectation of z square plus 2 times expectation of x into expectation of z. That is 0, right? So expectation of y square is p plus n, right? So if we know the expectation of y square, we can write the entropy f. Entropy is bounded by 1 by 2 log to the base 2 of 2 pi e into p plus n, right? So h of y upper bound we know and h of z we know. So we can write the information as half of log to the base 2 and then uh, these two when divided it will come as p plus n upon n, right? So this will be half log to the base 2 1 plus p by n. So this is the capacity of Gaussian channel, right? This is how we derive the capacity. Okay, so now next concept that I'm going to introduce is capacity of frequency flat deterministic MIMO channel. Frequency flat we have already discussed that. Now on moving onward towards MIMO we will be always taking frequency flat channels. Okay, and deterministic we will see that it is important that we know the channel. If the channel is not known, then it will be a different problem altogether. So deterministic is important. Okay, so this is frequency flat deterministic MIMO channel. Okay, so for MIMO we have suppose MT transmit antennas and MR receive antennas. Okay, and bandwidth we suppose as 1 hertz. Okay, and frequency flat, the channel is frequency flat over this bandwidth. Okay, so these are the MT antennas and these are the MR antennas of receiver. So the output is Y, that is MR plus 1 vector, that is given by square root of ES by MT. We have already discussed it, that the transmitter power is constant. right? We have to transmit es power only, but then we have to distribute it within the empty antennas. So at each antenna we have the square root of es by mt as the amplitude. Then we have h s plus n. This y is mr cross 1, so n is also mr cross 1 because there are mr receivers, so mr noises will be there. Then s is the transmitted signal from the antennas, so s is mt cross 1, and h is matrix. So this h is mr cross mt. We have already discussed all this, right? Now we take RSS as covariance matrix of S. That is expectation of S into S summation. Okay. And the mean of S is 0. Right. So suppose that the channel knowledge is there at receiver. Okay. So perfect CSI at receiver. Then what is the channel capacity? MIMO channel capacity. This would be given by C equal to maximum of information between S and Y, because S is the transmitted one, Y is the received one. Overall possible distribution of source, that is S. So now we compute the ISY. ISY is HY minus HY given S. Right. Then again we can write the Y as S plus N. Then H of S upon S is 0, and H of N by S is Hn because the noise is independent. We've already discussed. So this is Hy minus H of N. H of N we know because the noise is complex quotient. This is fixed. Right. So when we are finding the maximum of the mutual information, this is fixed. So we have to maximize entropy of Y. Right. So for maximizing mutual information, we have to maximize entropy of Y. Okay. So now you see y equal to s plus n is there. Now n is Gaussian. So y would also be Gaussian. So now we need to find the covariance matrix of y. RYY is expectation of y times of y Hermitian, right? This can be written as square root of es upon mt hs plus n into expectation of es upon mt. This would be s Hermitian h Hermitian plus n Hermitian, right? Now when we multiply the cross terms, you see first the expectation of S and N Hermitian, this will go as 0. Then again expectation of S Hermitian and N, this will again go as 0 because they are independent. So now we will be having two terms, expectation of ES by MT, H S S Hermitian, H Hermitian plus expectation of N Hermitian. Right. So now this is the significance of channel being known at the uh, CSI being known at the transmitter. Sorry, CSI being known at the receiver. This operation is happening at receiver, right? So H is deterministic. These are the S is random, right? So the expectation can crawl into this, right? So now we can write it as ES by MT H expectation of S is Hermitian H Hermitian plus this N into N Hermitian. This is fixed, okay? N is N1, N2, and so on up to NMR, and then N Hermitian would be like this. So the cross term would be 0 because the noises are IID random variables. So this will be like N naught like this, MR cross MR, right? So we can write it as N naught I MR, right? So this we can write as N naught I MR. Okay. So expectation of S Hermitian is given by RSS. So we can write it as ES by MT H RSS S Hermitian plus N naught IMR. Right. So this is RYY. Okay. And then we have HY equal to, like, entropy of Y equal to log to the base 2 and then determinant of pi e RYY. So we know that pi e to the power of MR it is, but then we have a theorem, right? I'll mention the theorem first. So if A is n cross n matrix and alpha is scalar, then determinant of alpha A is equal to alpha to the power n of determinant of A. So that is how we included the pi e term inside the determinant, because pi e to the power of MR would be determinant of pi, and then RYY is there. And Hn we know, this is log to the base 2 determinant of pi e, then n naught IMR, right? So information between S and Y, this will be equal to Hy minus Hn. Right. There is the maximum entropy for Hy. So when you divide this, it will be log to the base 2 and then determinant of this pi to the power n, and then pi to the power n will go cancel. So we can write it as determinant of RYY divided by determinant of N naught IMR, right? Now again we use this formula, right? So we can take it out as N naught to the power of MR. Okay. So we put the value of RYY, that is log to the base 2 of determinant of ES by MT HRSS H Hermitian plus N naught IMR divided by determinant of N naught IMR. Now you see, we divide by N naught here, and we take the this N naught outside. Okay, so N naught to the power of MR here and N naught to the power MR in denominator, that will get cancelled out, right? And this term will be then I plus ES upon MT N naught H RSS into H Hermitian. Right, this is information SY. Then capacity we can find as maximum of this term log to the base 2 determinant log to the base 2 determinant of I plus this. H into RSS into H Hermitian. Fine, okay. So we have to maximize the capacity such that trace of RSS equal to empty, because we need that the total power transmitted is ES only. So the trace of S into S emission should be empty. Okay. So this is how we find the capacity of MIMO channel. So this is the capacity of MIMO channel when CSI is known at receiver. So we saw the importance that when CSI is known at receiver, we just uh, put the expectation inside. If it is a random variable, then we cannot do that, right? So this is the capacity when channel state information is known at the receiver. Now two more cases are there. One is when the channel state information is unknown, and when the channel state information is known at transmitter as well. So we will see both of these in the next tutorial class when next week. Hopefully that will be the last one. So now two questions are there that are left. We will see that. Now we see there is a communication system where the channel between the transmitter and the receiver is AWGN. So this is mentioned that Gaussian channel is there. Okay. Then we have the average received SNR. This is equal to 5 dB. Okay, so we might want to convert it into linear scale. So this would be equal to 10 to the power 0.5. That is 3.162, I think. Then the maximum spectral efficiency. Spectral efficiency is C by B. That is bits per second per hertz. So the spectral efficiency is given by log to the base 2 of 1 plus SNR. This is log to the base 2 of 1 plus 3.162. That is log to the base 2 of 4.162. This is equal to 2.057 bits per second per hertz. Okay. So the answer would be D in this case. Now this is a good question. We have a 2 by 2 MIMO channel. The channel matrix is given. Average SNR is also given. SNR is given as 4 dB. That is, if we convert it into linear scale, that is 10 to the power 0.5. That is 2.5119. Okay. So the covariance matrix is given by RSS, but here RSS is identity matrix. So RSS is I2. Now the mutual information between transmitted signal S and received signal Y is asked. So mutual information between S and Y. This is given by log to the base 2 of determinant of I plus ES by MT N naught. ES by N naught is the SNR, right? SNR is given. MT is 2. Then H RSS H emission, right? RSS is I, so this will be H into H emission. So this will be equal to log to the base 2 determinant of I plus 2.5119 by 2. Then H into H emission. So when H into H emission you will do, this will be 0.52, 0.46, 0.46, 0.58. Okay, now you do the calculations. So that will come as log to the base 2 of 2.3235. That will come as 1.3354 bits. Okay, so answer is A. So this is how we calculate the mutual information for MIMO, and this is how we calculate the capacity. So we started from information theoretic perspective. We calculated we saw entropy, joint entropy, then Kullback-Leibler distance, relative entropy, and then we came to mutual information. And then we saw the entropy for normal distributions like bivariate and multivariate normal distributions, and then we saw that the entropy for multivariate or any variate normal distribution is the maximum, that is the upper bound. Okay, then we saw that the in that we used for the derivation of information, that is capacity. Like maximum of information is capacity. So like the today's class flow is like that, and I hope all the questions are clear. So this is it from my side. I think I'll see you next week. Okay then, bye.